what really happened during the Silurian. Today, we are venturing into a discrete era, often overshadowed, but nonetheless essential. A moment of respite after chaos, a time of slow, patient, fertile reconstruction. A world breathing anew, after having wavered. It's the Silurian, a fragile bridge between the past disaster and the worlds to come. About 440 million years ago, Earth was just emerging from a massive extinction. The ice caps were retreating, the seas were rising again, and in this lull, life regained its foothold and advanced. But before embarking on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a good journey. Throughout Earth's history, periods of massive upheaval have marked ecosystems, leading to successive extinctions and rebirths. The Llandovery, spanning from 443.8 to 433.4 million years ago, is an example of such a time. Situated at the beginning of the Silurian, after the end Ordovician crisis, it symbolizes the revival of marine ecosystems. Despite persistent instability, a warm climate and the absence of polar ice caps created conditions conducive to reclaiming habitats. We will explore the three subdivisions of the Llandovery: the Rudanian, the Uronian, and the Telecian. Each reflects a key stage in life's resilience, illustrated by the reoccupation of shallow reefs, species diversification, and the appearance of armored fish. The Rudanian, from 443.8 to 448 million years ago, inaugurates a period of reconstruction. The oceans, still marked by the previous crisis, harbor anoxic zones where black shales accumulate. However, incursions of better oxygenated water allow brief proliferation of organisms. Variations in sea level influence the distribution of fauna. Gradually, the submerged reefs and plateaus become suitable for life again, supporting new ecosystems and marking the beginning of the Llandovery's biological renewal. The fauna of Huangshi, discovered in southern China, bears witness to the slow revival of life. In occasionally oxygenated marine beds, sponges, cephalopods, and arthropods dominate. Sponges filter suspended particles and are adapted to fluctuating environments. Cephalopods, ancestors of octopuses and squids, demonstrate increasing trophic complexity. The highly diversified arthropods illustrate how biodiversity recovers. The resurgence of life occurs in waves, during periods more favorable for species diversification. As soon as the underwater plateaus become habitable again, groups like stromatoporoids and tabulate corals form new reefs. These structures provide refuge for many organisms, such as orthid brachiopods, which constantly filter water. Life quickly resumes, taking advantage of spots suitable for attachment and feeding. The preservation of these habitats in the geological record shows the adaptation of reef builders. Despite unstable conditions, they manage to build lasting structures, offering refuge to an expanding biodiversity, a few million years after the Ordovician crisis. Next comes the Uronian, covering from 440.8 to 438.5 million years ago. During this period, the sea advances further inland, promoting the colonization of new coastal areas. Dendroid graptolites, colonial organisms in the shape of small bushes, indicate fluctuations in sea level. Their abundance in certain layers attests to phases of marine expansion, where these planktonic animals disperse further. This group is essential for precisely timing the evolution of marine geography. Recent work on a global stratotype section and point aims to better define the chronological boundaries of the Uronian, allowing differentiation between local variations and global trends influencing ecosystems. In this quest for stratigraphic precision, scientists plan for 2024 to closely examine the reference section in the Czech Republic to clarify the boundary between the Uronian stages. Graptolites play a key role here, each species having a precise distribution in the sedimentary column, allowing for highly detailed layer identification. This approach, beyond its academic aspect, helps to understand the rhythms of sea level transgressions and regressions. Periods of rising seas, linked to temporary climate warming, reduce the extent of ice and alter coastal ecosystems. This opens new pathways for some organisms, while others are forced to migrate or disappear. The Telikian, between 438.5 and 433.4 million years ago, marks a key stage in the history of vertebrates. It is at this time that armored fish, such as Naxalepus and Zeuxinosteus, emerge in the red shales of Chongqing in China. The term armored refers to skeletal plates protecting the skull and front of the body against predators. The red shales, rich in iron oxides, indicate an oxygenated environment favorable for the preservation of anatomical details. The evolution of these fish reflects adaptations to food competition and predation. The appearance of mineralized exoskeletons marks an evolutionary turning point, transforming the ways of feeding, moving, and defending, while paving the way for increased diversification of fish in the Silurian. Eurypterids, or sea scorpions, undergo great diversification in the Telikian. These arthropods vary in size, from a few centimeters to more than a human arm. Fossils from the lagoon environment of Waukesha reveal the earliest marine scorpion, equipped with a potentially venomous sting, suggesting a common origin with terrestrial scorpions. They become major predators, adapting their spines and robust pincers to hunt various invertebrates and vertebrates. This diversification complicates food chains and energizes the Telikian ecosystem. The faunal renewal of the Llandovery is explained by a specific environment. High carbon dioxide levels, much higher than today's, maintained a warm climate. The continents, distributed differently, undergo intense precipitation, transporting nutrients and sediments to marine basins. This flow stimulates planktonic life, fundamental to many food networks. In shallow areas, light, warmth, and nutrients promote the growth of corals and sponges. However, anoxia persists in some regions, creating a contrast between areas rich in life and others almost deserted. Thus, the marine faunas of the Llandovery find a precarious balance between expansion and retreat. Reefs have played a stabilizing role in this cycle of alternations. By building durable structures, corals and stromatoporoids offer refuge to many species, maintaining the continuity of ecosystems despite environmental fluctuations. Orthid brachiopods, well adapted to fixation, establish in dense colonies, benefiting from the shelter of reefs. These assemblages then attract predators, such as boring mollusks or carnivorous arthropods. The preserved fossils reveal a mosaic of biotic interactions, making the Llandovery a natural laboratory where primitive forms and innovative lineages coexist. This mosaic reflects the ecological revival, redrawing niches and rebalancing competitive and predatory relationships. The transitions between the Rudanian, Ironian, and Telikian are distinguished by variations in sea level and ocean chemistry. Marine transgressions promote the migration of species, while regressions isolate certain basins, testing their adaptability. Groups capable of inhabiting different habitats, such as reefs or lagoons, fare better. Fish armors and arthropod shells protect them against predation. The Ironian lays the groundwork for diversification, and the Telikian realizes the rise of fauna. The Llandovery illustrates a phase of ecological reconstruction after the Ordovician crisis. From the Rudanian to the Telikian, this period demonstrates a strong biological dynamic, favored by a warm climate and high productivity. The study of the Llandovery reveals how life, despite the most severe crises, always finds ways to renew itself. Each fossil discovery enriches our understanding of the mechanisms of biological resilience. This chapter of the Silurian remains a fascinating example of adaptability and innovation in the history of life on Earth. The Wenlock, which spans from 433.4 to 427.4 million years ago, according to the latest geological and stratigraphic studies, marks a major stage of the Silurian. This period, often referred to as the reef and radiation period, witnesses a spectacular proliferation of marine life while being shaken by climatic and environmental upheavals. To grasp its full scope, one must explore its two substages: the Llandovery, from 433.4 to 430.5 million years ago, and the Homerian, from 430.5 to 427.4 million years ago. We will explore them chronologically, simplifying the concepts to make this era accessible to all. At the beginning of the Wenlock, the Earth, though having undergone several biological readjustments, still sees the marine world in a state of reorganization. The first phase of this era is distinguished by the explosion of reef ecosystems and associated faunas. During this period, regions like Baltica and Laurentia are covered with shallow epicontinental seas. In these warm seas, although the exact temperature is difficult to determine, some fossil evidence and geochemical studies suggest an average between 20 and 32 degrees Celsius. A notable phenomenon of this era is the formation of massive reefs created by stromatoporoids and corals, such as tabulate and rugose corals. Stromatoporoids, often confused with sponges, are marine organisms with an internal calcareous skeleton having a layered structure. The name stromatoporoid means layered structure due to the calcareous layers they secrete for protection. During the Llandovery, these organisms form massive colonies, creating bioconstructs that can reach several meters in thickness. These structures provide a habitat for various forms of life, like tabulate corals, cnidarians with distinct septa, which, together with the stromatoporoids, form giant reefs and support a flourishing biodiversity. The flourishing of reefs benefits many species, such as brachiopods and other shell-bearing organisms that filter water to feed. These animals possess a lopophore, an organ with ciliated tentacles to capture suspended particles. Although they resemble bivalve mollusks, brachiopods have upper and lower shells. Their diversity is particularly high in the Llandovery reefs, favored by a warm climate and rising sea levels, submerging continental shelves. In these seas, the underwater landscape is composed of plateaus covered with reefs, forming barriers that protect other species by dampening wave forces. At the foot of these structures, life abounds with crustaceans, mollusks, and resilient sponges. The Llandovery is a prosperous marine phase where food, light, and environmental stability promote major biological growth. The radiation of marine life is not uniform, as the distribution of land and seas depends on the repositioning of continental masses. Baltica and Laurentia often illustrate these giant reefs, typical of the era. Geologists and paleontologists search for fossils that testify to life on these paleocontinents. Fossils, such as calcareous stratifications and brachiopod shells, inform us about the ocean chemistry of the time. This is done through the analysis of carbon and oxygen isotopes, revealing information on temperature, biological productivity, and carbon dioxide. During the Woodian, conditions remain favorable, although the Earth undergoes small-scale sea level fluctuations and climatic variations. The Silurian is often described as a period of moderate greenhouse effect, with carbon dioxide levels higher than today, but less extreme than in other Paleozoic eras. The prosperity of reefs and shallow waters reflects these tempered conditions and the retreat of continental glacial structures, which were more developed earlier. The Woodian of the Wenlock is distinguished by its giant stromatoporoid coral reefs. The increase in filtration zones and the structuring role of these ecosystems lead to an explosion of marine diversity. The filtering shells of brachiopods multiply on the submarine plateaus, showing a real ecological opportunity. However, this prosperity is accompanied by fragilities, particularly sensitive to environmental disturbances. At the transition between Woodian and Homerian, signs indicate that the Earth will experience significant changes, to which many species will not survive. After the Woodian, the Homerian is marked by the Ordovician extinction event, which disrupts marine fauna, notably two groups essential to Paleozoic stratigraphy and evolution, the conodonts and graptolites. To grasp the magnitude of this event, it is crucial to understand the importance of these two groups of organisms. Conodonts are tooth-shaped mineralized structures found as microfossils in marine sediments of the Paleozoic and Mesozoic. Although their animal nature was long debated, it is now known that they were part of a group of primitive vertebrates with dental elements used for feeding. They serve as guide fossils, allowing for the dating of geological layers. During the Ordovician event, about half of the conodont species went extinct, signifying a major ecological crisis in the Silurian. Graptolites are colonial pelagic animals that float or swim freely in the water column. Despite their peak in the Ordovician, they are still found in the Silurian. Their filamentous or ribbon-like segmented structures represent individuals of the colony. They filter tiny particles and plankton, and their wide geographical distribution makes them good chronological markers. The Ordovician extinction leads to a loss of nearly 50% of the graptolites, affecting plankton and the pelagic food chain, thus altering ecosystems. The Ordovician event is not limited to the extinction of species. The rocks reveal a positive excursion of organic carbon, indicating an increase of carbon isotope 13 in relation to isotope 12. This indicates significant changes in the carbon cycle related to modifications in oceanic productivity, sedimentation patterns, or the expansion of anoxic zones. These fluctuations are accompanied by eustatic variations in sea level, influencing the distribution of coastal environments, reefs, and the survival of species over hundreds of thousands of years. Sea level changes can result from several factors. One of the main ones is the growth or melting of ice caps that store water on continents. Tectonics, less marked at this Silurian time, also plays a role as continents collide and modify the geometry of ocean basins. During the Wenlock, tectonics is important, as the continental blocks of Baltica, Laurentia, and other territories slowly move, forming mountain chains and altering regional climates. The Ordovician event unfolds in a context of multiple changes: the drop in the diversity of pelagic groups, carbon modifications, sea level fluctuations, and possible effects on reefs. As is often the case during crises, not all regions are equal, with some areas developing niches favorable to certain lineages. The stromatoporoid coral reefs, although affected by the decrease in biodiversity, remain present. Brachiopods and other filter organisms maintain stable populations or reorganize on more limited substrates. The marine ecosystems of the Homerian show resilience in the face of the partial extinction of key groups. To better understand the chronology and scale of these upheavals, scientists have analyzed new isotopic records in several regions. This is notably the case with recent research conducted in Yunnan, a province in southwest China, which exhibits geological outcrops rich in Silurian marine fossils. These specialists are able to carry out high-resolution analyses there, scrutinizing rock sections centimeter by centimeter to observe isotopic changes with precision. Carbon isotopes, along with those of oxygen and sulfur, allow for the reconstruction of climatic episodes over periods limited to tens of thousands of years. In the middle of the Homerian, there is talk of millennial climate cyclicity, where cycles repeat every 1 to 2,000 years. Researchers in Yunnan, in a study, identified several of these cycles, associated with variations in sea level, water oxygenation, and fossil distribution. Their method relies on the observation of well-preserved sediments and the use of advanced mass spectrometry techniques. Through microscopic and sophisticated approaches, a clearer picture of the Homerian emerges. We better understand the order of events. The Ordovician crisis, marked by the extinction of conodonts and graptolites, followed by small-scale climatic variations that alter certain ecological pressures. Reefs undergo influences that sometimes cause retreat or slow transformations. The biological imprint of this Wenlock period remains marked by how life adapted or disappeared in the face of these upheavals. In this visual framework, seas traverse coastal areas whose contours evolve according to eustatic oscillations. The giant reefs from the early Wenlock still exist, but organism skeletons show signs of environmental stress. Discontinuities and changes in the sediments suggest variations in water quality and depth. In response to these changes, some species migrate or go extinct, while opportunistic groups diversify and colonize the freed niches. The ecological balance evolves, thus influencing the future paleontological history. When focusing on extinction, one often imagines a sudden cataclysmic crisis, but the reality is more gradual. Paleo-environmental crises operate in waves. Episodes of oxygen scarcity exacerbate local mortality, followed by reoxygenation phases where some species return. These alternations are related to altered ocean currents, upwelling, or the configuration of continents that influence water movements. In the Homerian, the complexity of these variations explains the enduring disappearances of some lineages and the resilience of others. For an audience discovering these phenomena, one must imagine that the Earth, although different from today, follows the same laws of ecology and climate. Species evolve within tolerance limits, and a rapid environmental change can trigger chain reactions. The Ordovician event shows that breaking conditions like water chemistry and sea level disrupts key species in the water column. This impacts trophic networks, where the disappearance of microfossils can indirectly affect larger animals. Despite the biological losses, the Homerian is a time of innovation and consolidation of adaptations. In the reefs and on marine terraces, new types of brachiopods, mollusks, and other invertebrates take advantage of the vacant niches. The first fish, appearing timidly earlier, gradually colonize marine cliffs, supported by the improvement of their skeletal systems. The Silurian is often seen as the period foreshadowing the great diversification of vertebrates and the conquest of terrestrial environments. However, in the Homerian, aquatic species still dominate. Confronted with this sight, current scientific research is crucial. Recent analyses of geological samples, notably in Yunnan and elsewhere, provide us with more precise data on dating and the chemistry of the ancient ocean. Some resolutions go down to less than 20,000 years, a remarkable precision on a geological scale. Within the Homerian, different ecological pulses stand out, like a fossil electrocardiogram, where fluctuations in carbon dioxide and temperature cause stress, while stable periods promote small innovations. The end of the Homerian around 427.4 million years marks the transition to the following Silurian. The reefs, though still present, are modified. Marine communities have evolved. Some lineages of conodonts and graptolites have diversified or specialized, while others have disappeared. Paleontological analyses also reveal the transformation of many invertebrates, such as brachiopods, corals, sponges, and planktonic microorganisms. The great lesson of the Homerian is the fragility and resilience of life. Recapping our dive into the Wenlock, the Woodian marks the formation of stromatoporoid coral reefs, accompanied by a flourishing fauna of shell-filtering organisms with lopophores. The shallow marine platforms of Baltica and Laurentia become underwater oases, where biodiversity thrives, thanks to stable environmental parameters. Brachiopods and other filter feeders benefit from this bounty, while corals build superstructures housing diverse communities. The transition to the Homerian sees the Ordovician extinction, reducing conodonts and graptolites by at least half, leading to geochemical upheavals and a gradual reorganization of populations. Ongoing work, notably in Yunnan, clarifies the pace of these variations. Isotopes once silent in ancient rocks are now revealed through modern technologies, highlighting short and intense cycles during the Homerian. These studies show that the Silurian Earth was not static, but was already undergoing recurring climatic and chemical battles over a few million years. The Wenlock thus appears as an exciting chapter of life's history, whose stakes curiously resonate with current environmental challenges. This adventure in the Wenlock reminds us that ecosystems are shaped by matter, energy, climate, and time. The giant reefs illustrate the power of organisms that, through their occupation of space and access to food, modify the marine geography. Extinction crises often result from external changes, such as sea level variations, or internal changes, like shifts in ocean chemistry and food networks. The Wenlock, despite its upheavals, laid a solid foundation for the subsequent expansion of life. We are plunged into a distant era, that of the Ludlow, a significant subdivision of the Silurian, spanning from about 427.4 million to 423 million years ago. This decisive moment sees environmental upheavals and notable biological adaptations. It is nicknamed Crises and Conquest of the Shore, as it marks both partial extinctions and the continued expansion of life toward coastal and littoral areas. To better understand these few million years, we will travel through time and create as comprehensive a picture as possible. We will see how marine organisms underwent major disturbances while exploring new spaces, how some creatures grew larger, and how modern research sheds light on each new discovery. Settled into our role as observers, we will begin by studying the two key subdivisions of the Ludlow, the Gorstian and the Llandovery. At the beginning of the Gorstian, the continents are arranged differently, and the atmosphere, rich in oxygen, presents higher carbon dioxide levels. The climate is generally warm, without permanent ice caps, although local fluctuations and disturbances exist. The omnipresent shallow seas are the cradle of numerous biological communities. This marine environment, subject to variations, witnesses progressive rearrangements in the composition of the fauna. In these vast stretches of water, numerous biological groups thrive: sponges, algae, corals, brachiopods, mollusks, and arthropods. The first reefs of this era begin to resemble true natural barriers, playing a crucial role by offering habitats for biodiversity and protection against waves. Although far from the abundance of modern reefs, this period marks a notable expansion of reef structures dominated by species filtering the water and forming colonies. When discussing the Gorstian, it is essential to mention the Mulda event. The term Mulda refers to a geographic site where the geological strata allow this phenomenon to be studied. During this event, what paleontologists call a turnover of graptolites is observed. These small planktonic organisms live in colonies and often appear as rods or fossilized saws, clearly visible in ancient marine rocks. The term turnover refers to species rotation. Some disappear, others take their place. In this case, several species of graptolites go extinct, while new forms appear or spread, indicating an ecological rearrangement due to environmental changes. The impact of the Mulda event is not limited to graptolites. Researchers also note a general decline in pelagic biodiversity, meaning organisms living in open water far from the sea floor. This decline could be linked to episodes of hypoxia or variations in parameters such as water temperature and salinity. However, during the same period, the extension of barrier reefs, vast formations constructed by sessile organisms like corals or other invertebrates with calcareous skeletons, is observed. This expansion highlights the diversity of biological responses to crises. While some species decline, others take advantage of new opportunities for settlement and growth. In the Herefordshire region, a geological formation called Lagerstätte has yielded remarkably well-preserved fossils. The German word Lagerstätte, meaning storage place, refers to an exceptional fossil site. This formation is especially known for its record of diverse marine organisms dating from the Silurian. At the heart of this deposit, Herefordia appendiculata, a small bivalve-shelled arthropod, was discovered. Ostracods, tiny crustaceans common in the history of marine life, are often found with their mineralized shells, but rarely with their appendages. Herefordia appendiculata stands out with exceptionally well-preserved appendages. Thanks to synchrotron tomography in 2024, scientists have been able to create a three-dimensional representation of these appendages. Synchrotron tomography uses a particle accelerator to produce highly energetic electromagnetic radiation. This radiation allows the reconstitution of the internal structure of fossils that are difficult to extract. By studying the limbs of Herefordia appendiculata, paleontologists have gained a better understanding of the evolutionary position of the Binoticopes, a group of ostracods with distinctive traits. This discovery has clarified their mixed behavior, capable of swimming and moving on the bottom, with morphology adapted both for locomotion and feeding. As the end of the Gorstian approaches, marine ecosystems seem to be gradually transforming. Barrier reefs expand in stable areas where nutrients are sufficient. However, a great local variability persists. Some regions still experience fluctuations in oxygen and chemical changes, making life more fragile. Graptolites, whose organization in planktonic colonies depends on ocean currents and chemistry, continue their evolution. New forms appear in fossils, but overall, this group remains vulnerable to decline if conditions deteriorate. Ostracods, on the other hand, exhibit great diversity despite constraints. They adapt to different habitats by modifying their size, carapace ornamentation, and diet. With the Llandovery, Earth enters a new phase in the history of the Silurian. While the Gorstian has already experienced disruptions, the Llandovery is also characterized by significant phenomena. This period is associated with large fluctuations in sea level and changes in the chemical balance of waters, testifying to complex climatic mechanisms. In the Llandovery, continental plates continue their slow movement. Orogenic collisions, which form mountain ranges, influence relief, the formation of sedimentary basins, and the distribution of epiric seas. These phenomena have a direct impact on the distribution of marine fauna and the development of coastal ecosystems. In this constantly evolving context, life faces episodes of anoxia, where the lack of dissolved oxygen in the water affects species. Some can tolerate brief episodes of anoxia, while others disappear or seek new refuges. The Llandovery event, which we will now examine, is one of these major anoxic episodes. The Llandovery event is an episodic anoxia, where the oxygen content in certain oceanic zones decreases and then increases over a geologically short period. These oscillations may be due to climatic changes, sea level variations, or imbalances in the production and decomposition of organic matter. A key indicator for measuring the extent of the disturbances is the carbon isotopic composition in rocks. Instead of using complex symbols, we call it delta 13 carbon, which represents the distribution of carbon isotopes in sediments. During the Llandovery event, a delta 13 carbon peak of +9 per mil indicates a significant change in the global carbon cycle. This fluctuation is related to a modification of the ratio between organic carbon and mineral carbon. Simultaneously, we observe a decline in crinoids and stromatoporoid brachiopods. Crinoids, relatives of starfish and sea urchins, filter plankton with their feathery arms. Stromatoporoid brachiopods have a flat and wide shell, which they use to anchor or rest on the seabed. Their decline likely reflects the combined impact of anoxia and environmental changes on their lifestyle, particularly water filtration and access to nutrients. The Llandovery event, although not as famous as other mass extinctions, caused a significant reorganization of marine fauna. It shows that even during relatively stable periods, disturbances can lead to localized or regional extinctions. Resilient species, capable of tolerating oxygen variations, survive and spread as the less adapted ones disappear. This phenomenon, where the crisis of some life forms paves the way for the diversification of others, is a key aspect of evolution. Despite these crises, or perhaps thanks to them, some marine organisms thrived during the Llandovery. This is the case for the tiergotides, large eurypterids whose impressive morphology is striking. Eurypterids are predatory arthropods living mainly in aquatic environments. Throughout their evolution, they have adopted various forms and sizes, ranging from modest creatures a few centimeters long to giants over 2 meters in length. During the Llandovery, we observe gigantism in the tiergotids, with specimens exceeding 2 meters. Recent discoveries published in 2024 have uncovered new Australian fossils, confirming this gigantic size. These specimens show that these arthropods, far from being confined to a single region, could have widely migrated across the supercontinent Gondwana. To understand the impact of these creatures, it's important to note that the Silurian marine ecology was not solely dominated by evolved fish, as in more recent ecosystems. The tiergotids, with their strong pincers and locomotion ability, were major predators, probably occupying the top of the food chain. Their size suggests that they could attack smaller arthropods, mollusks, and even primitive fish. The fact that they measured more than 2 meters suggests they had specific adaptations for breathing, moving, and hunting. Some paleontologists believe these pitayergotids may have developed structures to move in shallow waters or even approach shores, tracking prey in areas where land and sea meet. The marine level variations during the Silurian would have facilitated this behavior by periodically liberating or flooding coastal surfaces. The term trans-Gondwanan refers here to the dispersion of tire-gotids and probably other taxa across the supercontinent Gondwana. The latter included the southern hemisphere, including South America, Africa, Antarctica, Australia, and India. The presence of pitayergotids, over 2 meters long in various parts of the supercontinent, shows a great dispersal capability. The climatic and eustatic variations of the time probably allowed the regular opening and closing of marine corridors, enabling pitayergotids to cross natural barriers and colonize new spaces. Some paleontologists suggest that their gigantism could have been caused by abundant resources in lagoons or nutrient-rich coastal seas. Where other faunas suffered crises, the pitayergotids would have taken advantage of temporarily vacant ecological niches. Large-scale migrations do not occur instantaneously. They span several hundreds of thousands of years. Although this is short on a geological scale, it represents many biological generations. The presence of giant specimens at different sites shows a complex planetary dynamic, mixing climatic factors, continental drift, and ecological evolutions. Any ecological crisis leaves traces. Families decline, species alter their geographical distribution, and newcomers occupy available niches. After these crises, there is often a temporary reduction in diversity, followed by a phase of recolonization and diversification. Crises can be fatal for sessile organisms such as corals, sponges, or fixed brachiopods if they alter the composition of the water or the height of the water column. Transient anoxia represents a major challenge since corals and their symbionts require oxygen and other specific resources. In contrast, more mobile animals, capable of moving to better oxygenated waters, have a larger survival window. Crinoids, which filter water for nutrition, experienced decline in the Llandovery during the Ludlow event due to the deterioration of water quality. Strophominid brachiopods, on the other hand, cannot withstand excessive fluctuations in oxygen and nutrients, leading to their decrease in the fossil layers of this period. In contrast, Eurypterid arthropods, including the giant pterygotids, are considered more opportunistic and resilient, taking advantage of less competitive areas. The evolution of the coastline, with the lowering and rising of sea level, creates new shores that certain species explore. Ecological niches gradually appear in poralic environments, close to coasts. The emergence of brackish waters and lagoons favors organisms tolerant to salinity variations, thus offering opportunities to the most adaptable invertebrates. Advancing near the coasts fosters multiple interactions between species that colonize these margins. For example, primitive terrestrial arthropods, which begin to venture out of the water, find themselves in competition with other semi-aquatic life forms. Although terrestrial life is still nascent in the Ludlow, we can imagine that the rapid transformations of the littoral zone contribute to the establishment, a bit later, of true terrestrial ecosystems. The conquest of the shore is not instantaneous. Before the appearance of forest vegetation or animals with lungs on the ground, millions of years of evolutionary experimentation are needed. However, in the Silurian, the first signs of this dynamic emerge. Marine organisms that tolerate shallow depths, like some armored fish or eurypterids, adapt to brackish waters and hunt various prey in transitional environments. Our knowledge of the Ludlow comes from rocks and fossils discovered around the world. By using several analytical methods, such as stratigraphy, paleontology, and geochemistry, we gradually reconstruct the puzzle of this distant era. High technology now transforms these investigations. Thanks to synchrotron tomography, we can observe in 3 dimensions the morphology of fossils embedded in rock. Finer techniques also measure the isotopic ratios of carbon, oxygen, and sulfur in sediments. These variations are essential indicators for tracking the evolution of environmental conditions, such as biological productivity or the extent of anoxic waters. Paleogeographic mapping, which reconstructs the position of continents at a given time, is becoming more refined. They shed light on the migration pathways of faunas to disperse from one region to another. These combined approaches allow us to more precisely address biological crises and biodiversity expansions, and to understand how the dynamics of life adapt to the planet's physical changes. During the Lau event, the importance of sedimentary deposits rich in organic matter becomes evident. In some regions, the low oxygen content prevents the complete decomposition of organic debris due to a lack of an effective aerobic bacterial community. This partially degraded organic matter gradually transforms, over millions of years, into fossil rocks. Sea level variations influence the deposition of sediments in marine basins. When sea levels fall, rivers bring more materials to continental margins, increasing coarse particles in the strata. Conversely, when sea levels rise, fine deposits dominate, sealing the underlying layers and sometimes trapping pockets of oxygen-poor waters. By examining such formations, geologists identify anoxic signatures in rocks, such as pyrites, which result from sulfate reduction and indicate a lack of oxygen. The Lau event, beyond its impact on fauna, left a particular sedimentary legacy, visible in stratigraphic sections from various locations around the globe. The Llandovery is not just a period of crisis, it's also a time conducive to certain expansions. While some faunas decline, others proliferate. Tabulate corals, for example, show resilience and quickly recolonize areas vacated by the extinction of other organisms. Calcareous algae also take advantage of warmer waters to grow and contribute to the formation of reef masses. The microscopic world undergoes changes, with microfossils like spores and plankton serving as indicators of major environmental changes. Their size, diversity, and distribution evolve from one geological layer to another, showing the evolution of the Silurian ocean. These alternations between crises and radiation manifest repeatedly in Earth's history. They underscore the resilience of life, which continues to reorganize despite obstacles. In hindsight, we better understand the legacy of the Ludlow. The fossils found in its layers testify to a changing world, preparing for the future diversification of marine and terrestrial ecosystems. The Mulda and Lau crises remind us that stability is merely an illusion. Earth has always been marked by great fluctuations, redefining biodiversity through a constant process of disappearance and reinvention. However, talking about crisis should not overshadow the creativity of evolution. Faced with an environmental change, a species can disappear or adapt. This gives rise to new forms, ecological strategies, and ways of life. The Silurian underwater landscapes thus prepare for the revolution at the end of the Paleozoic, where fish and terrestrial plants will become dominant, heralding the spectacular conquest of continents. At the end of the Llandovery, despite occasional episodes of anoxia, life continues to populate the ocean floors, forming diverse communities. Graptolites, though declining, still have some representatives. Ostracods remain prolific, and large eurypterids roam the currents in search of prey. If one were to paint a picture of the Llandovery Ocean at the end of the period, one would see coral reefs traversed by channels where light is diffuse and deep zones where stagnant waters accumulate organic matter, depriving fauna of oxygen. Despite these contrasts, the silhouette of a tire gotted in the clear waters would be striking, witnessing the power of natural selection and the potentialities of life in the face of changing environments. Beyond the descriptive, the end of the Ludlow fits into a long-term trajectory. The transition to the Pridoli will see the development of pioneering terrestrial plants and increasingly evolved fish, continuing the conquest of the shoreline and initiating the diversification of jawed vertebrates. However, this brings us to other chapters of the history of life. To conclude our exploration of the Ludlow, and more precisely its subdivisions, Gorstian and Llandovery, it is important to highlight the richness of this period. Among the significant events, we observed the Molde event and its graptolite turnover, as well as the drop in pelagic biodiversity and the expansion of barrier reefs. We followed the ostracod Herefordia appendiculata, whose appendages were revealed in 3 dimensions by synchrotron tomography. Finally, the Lau event caused episodic anoxia and a carbon-13 delta peak, affecting groups like crinoids and strophomonid brachiopods. Despite these crises, nature endures. The gigantism of tire gotids shows that with the scarcity of certain species or the release of ecological niches, other taxa gain in size and dominance. Trans-Gondwanan migrations testify to this world in motion, where dispersion and adaptation were essential. By studying this period of major upheavals, we can gain geological wisdom. Environmental balances, as stable as they may seem, remain dynamic and prone to shifts. Crises may repeat, but life, resilient, constantly diversifies and adapts. The Ludlow perfectly illustrates this dance between the Earth and its organisms. Over millions of years, partial extinctions give way to new expansions, and the organisms that survive are often those that quickly adapted to ocean changes or predation pressures. The Ludlow illustrates the complexity of marine evolution, marked by crises such as the Molde and Lau events, but also by resilience and biological innovation. The gigantism of pterygotids and the diversity of ostracods testify to this dynamic. Thanks to technological advances, we today perceive more finely the upheavals of this era, which prepare the future diversification of marine and terrestrial ecosystems. This period remains a fascinating chapter where life dances with the changing forces of the Earth. During the Pridoli, between 423 and 419 million years ago, a major transition unfolds on Earth. Still at the end of the Silurian, a period marked by marine upheavals and exceptional biological innovations, the living world crosses a new threshold towards the conquest of emerging lands, while marine ecosystems continue to transform. The Pridoli bears witness to this dynamic. On one side, the first pioneering microforests emerge, and on the other, fish with articulated jaws appear, offering new avenues of adaptation. Simultaneously, sea levels decrease, causing a planetary regression. This drop weakens reefs, which gradually disintegrate, while groups like the eurypterids decline in number and diversity. These evolutions fit into a complex chronology where each element finds its place in the history of terrestrial evolution. To understand the importance of the Pridoli, one must first situate the Earth in its context. In the Silurian, the planet benefits from a mild climate without large permanent ice caps. The carbon dioxide level, much higher than today, creates a moderate greenhouse effect, favoring warm and humid conditions. At the end of the Silurian, eustatic fluctuations appear. During the Pridoli, this trend reaches its peak with the gradual withdrawal of the sea, forcing marine ecosystems to adapt to new coastal landscapes or move to deeper waters. The reefs, especially those constructed by stromatoporoids and tabulate corals, bear the full brunt of the decline in sea level. These reefs, essential to Silurian marine ecology, sheltered many species and served as natural barriers against waves. When the water recedes, these reefs find themselves exposed to constraints like temperature and desiccation, disrupting their balance. The stability of these ecosystems is called into question, and although some remnants persist, they no longer have the same scope or vitality. These stratigraphic changes help paleontologists date the geological layers of the Pridoli. In parallel to the marine upheaval, another major phenomenon emerges: plant life on the continents. In the Pridoli, pioneering microforests appear, small but revolutionary. The genera Cooksonia and Baragwanathia are examples. Cooksonia is one of the first vascular plants discovered in the fossil record. Although it is small and leafless, it has tracheids, tissues capable of conducting water and nutrients. These tissues form the basis of vascular systems, which will later become more complex to give rise to larger plants. Baragwanathia presents more complex structures, such as proto-leaves, and a more advanced conductive system. The cryptospores demonstrate its ability to reproduce on emerged soils, while the cuticles and stomata attest to its management of gas exchanges, crucial in a drier environment where water is no longer abundant. The cuticles prevent water loss, and the stomata regulate gas exchanges. The ability to survive out of water marks a turning point, gradually enabling the colonization of the terrestrial surface. This stage is crucial biologically because the establishment of plants on soils marks the birth of terrestrial ecosystems. The first microforests of the Pridoli, formed of low plants on small sediment mounds, contribute to the formation of new soils by retaining water and promoting the development of microbial communities. The roots, or first anchoring systems, hold the particles of soil, creating a primitive humus. The accumulation of organic matter produces thicker soils where new species can settle. This process of conquest is slow but decisive. As the pioneering plants begin to green some shores and plains, a major evolutionary leap occurs in the waters of the Pridoli, the appearance of fish with articulated jaws. Before this, most fossil fish had rudimentary structures without complex jaws. The species of Entelognathus show how jaws become more complex, offering new modes of feeding. The first acanthodians, known as spiny fish, also appear. This evolution profoundly changes the dynamics of marine ecosystems, with new types of predation and selective pressures encouraging other animals to defend themselves or develop survival strategies. With the rise of more efficient fish, the eurypterids begin their decline. These giant arthropods were super predators in the Paleozoic marine ecosystems. They inhabited coastal waters and shallow lagoons, where some species reached over a meter and exerted strong pressure on many animals. However, approaching the Pridoli, several factors such as marine regression and competition with jawed fish reduced their number and diversity. By the end of the Silurian, their ecological role is less pronounced. To measure the impact of these upheavals, paleontologists analyze the rocks and fossils of the Pridoli. Stratigraphic study observes sediment layers, each layer containing fossil remnants of the fauna and flora of the era, as well as traces of water chemistry and climate. Specialists detect the regression by identifying coarse sediments, typical of coastal environments, and the rarity of certain corals. The discovery of fossils of Cooksonia or Baragwanathea shows the progression of vegetation and the diversity of cryptospores. These clues coincide globally, confirming a widespread phenomenon. The term pioneering microforests can be misleading, but these microforests do not exceed a few centimeters in height. The expression is justified because they form a dense mat of stems and small assimilative structures, creating a plant cover that modifies ground luminosity. This allows certain small terrestrial or semi-terrestrial invertebrates to find refuge. Although fragmentary, this marks the dawn of more complex ecosystems where the recycling of organic matter begins. The roots, even rudimentary, help fracture rocks and create new soils, and lichens play a crucial role in preparing substrates. At the same time, the fish of the Entellognathus lineage, equipped with prominent skin plates and a robust jaw, begin to diversify. Fossil fragments discovered in certain formations show that these fish vary in size, from small forms to larger individuals, armed with bony plates on the head and thorax. This is one of the first signs of a future explosion of diversity among jawed vertebrates, which, over the following eras, will give rise to modern fish groups and tetrapods. The first acanthodians already exhibit notable features. Their fins are supported by sturdy spines, and they seem to have varied diets. Some have conical teeth, suggesting they fed on small arthropods or larvae, while others could feed on plankton or organic particles. Their presence marks the end of the era of jawless fish and the advancement of the complexity of trophic networks. The general eustatic regression of the Pridoli reveals changes in sediment and nutrient dynamics of marginal marine basins, creating areas of increased productivity or resource poverty. Marine organisms dependent on these supplies react differently. Some corals, weakened by variations in salinity or temperature, do not survive the lowering of sea level. Stromatoporoids experience a contraction in their distribution range. Reef ecosystems lose their role, freeing up space for more mobile organisms. From a paleo-environmental perspective, talking about the march towards land may seem paradoxical while life remains primarily aquatic. Yet, geological and fossil evidence confirms a turning point. Plants with vascular structures rise for the first time out of the water, and some arthropods evolve in nascent terrestrial environments, likely to feed on plant debris or microorganisms. Although marine life still predominates, this marks a turning point in the history of life. Eurypterids are indicators of the health of coastal and lagoon ecosystems. Their gradual decline suggests a lack of prey, a less favorable habitat, or increased competition with other predators. New fossils from the Pridoli show specimens still of respectable size, indicating a gradual extinction. This rarity is measured by comparing deposits from the beginning of the Pridoli with those from the end or dawn of the Devonian. It is reflected in the decline of supernumerary species, while others, more specialized, survive in micro-refuges. At the dawn of the Devonian, their role becomes secondary, although some giant eurypterids will persist. In parallel, other geological evidence informs about the transformation of continental shelves. Regression not only means a retreat of the coastline, but also modifies sedimentation, erosion, and living conditions of organisms. Marine deposits become more discontinuous, and limestone layers transform into siltstones or red shales, marking the transition to more continental or lagoon environments. Fish fossils are sometimes found in levels of ancient estuaries, confirming some species' ability to adapt to salinity variations. This allows them to survive during low sea level periods. The climatic fluctuations of the Pridoli are also important. Although there are no major glaciers, slight temperature changes can influence the distribution of fauna and flora. A variation in water temperature can favor or penalize certain species, especially if it alters the dissolved oxygen level. Shallow seas, where water circulation is less efficient, are particularly sensitive. Some regions may experience anoxic episodes, leading to massive mortalities. The fate of stromatoporoid reefs depends on water chemistry, light, and nutrient inputs. Eustatic regression may bring more terrigenous sediments into marine areas where reefs develop, making the water turbid and reducing the photosynthesis of symbiotic corals. More resistant organisms can survive in turbid water, but overall diversity decreases. Pridoli formations show chemical signatures that confirm these terrigenous inputs, proving that reefs disappear not only due to sea level drop, but also because of environmental disturbances. As these changes occur, life on the emerging lands progresses slowly. Cryptospores, essential to the study of plant reproduction, become more varied in continental deposits. Their structure reveals patterns related to plant dispersion. Stomata show that water management and respiration adapt to the aerial environment. On some fossil stems, traces of cutin appear, protecting the plant from desiccation. Researchers estimate that these Silurian plants could already regulate their water balance and gas exchanges, an advancement for the conquest of the continents. At this time, terrestrial landscapes are not very lush, consisting mainly of rocky debris, clays, and decaying organic matter. Pioneering microforests slowly extend, mainly along shores or in marshy areas where moisture remains sufficient. The dried-up areas still undergo erosion, and winds carry away dust and sand, creating landscapes alternating dunes and vegetation. It is only later, in the Devonian, that true forests will emerge, dramatically altering the interactions between the atmosphere, hydrosphere, and lithosphere. Meanwhile, jawed fish, whose first signs of adaptation appear in the Pridoli, continue their diversification in the Devonian. The ancestors of sharks, rays, bony fish, and even tetrapods find their roots in the late Silurian and early Devonian lineages. The physiology of the jaw, the robustness of the dermal skeleton, and the arrangement of fins lead to major ecological innovations. The predatory function is enhanced by stronger jaws, and locomotion benefits from more mobile fins, gradually heralding the straightening of limbs in some vertebrates. It is essential to emphasize the importance of combining paleobotanical studies with organic geochemistry to understand this phase of Earth's history. Fossil plant remains can be analyzed to determine their chemical composition, lifestyle, ambient humidity, and light intensity. Recent research suggests that radial growth of stems may have begun as early as the Silurian in rudimentary forms. The evolution of more robust vessels would result from water fluctuations, and this balance between light capture and adaptation to the aerial environment encourages the appearance of features unknown to marine algae. The conquest of emerging lands during the Pridoli does not result from a single species, but from coordinated innovations among plants. Small vascular plants and adaptable arthropods begin to colonize the soils as the sea withdraws from some basins. The first terrestrial food chains take shape, still rudimentary, including mosses, lichens, detritivores, herbivores, and decomposing microorganisms. Gradually, these communities create sustainable ecological cycles, initiating the emergence of a whole new balance in the biosphere. In this same vein, it is interesting to note that marine life, far from collapsing, continues to explore various ecological niches. Armored fish appear and diversify, while acanthodians, sometimes fragile-looking, establish themselves in coastal waters as witnesses to the faunal renewal. Invertebrates remain dominant in terms of species number, but vertebrates are gaining more and more ground. In the background, the gradual decline of eurypterids marks the end of a supremacy and shows that competition among aquatic predators is turning in favor of the new fish. The Pridoli thus plays a role of denouement for some marine groups and introduction for other forms of life, better adapted to the changes. During this period, sediment flows, ocean currents, and the configuration of continents converge or fragment. Tectonic plates generate reliefs and reorganize ocean basins, while mountains form through collisions between microcontinents. These interactions influence atmospheric circulation and climate. The marine regression of the Pridoli could be related to mountain formation and variations in carbon dioxide. Emerging ocean rocks undergo increased erosion, capturing carbon dioxide, which could reduce greenhouse gases, leading to cooling or sea level fluctuations. The Pridoli, despite its brevity, leaves a considerable legacy. This period prepared the Earth for the Devonian, marked by the expansion of forests and the proliferation of fish. Without the pioneering microforests, the emergence of the first vertebrates with articulated jaws and the adjustment of marine ecosystems would not have been possible. The Pridoli serves as a transitional phase, closing the chapter on a Silurian dominated by reefs and superpredator arthropods, while opening up a more green and diverse planet. This final subdivision of the Silurian captures the attention of many researchers. Each year, new excavations and analyses refine our understanding of the Pridoli, acanthodian fragments, study of Silurian stems with tracheids, or sediments indicating marine retreat. With each new piece of data, the picture becomes clearer, revealing a period more complex than it seems. What was thought to be the end of the Silurian actually hides the beginnings of terrestrial conquest, heralding the appearance of organisms adapted to life on land. The study of the Pridoli helps us understand how this evolutionary crossroads paved the way for critical thresholds in the biosphere, both in water and on land. The Pridoli symbolizes a decisive moment in the history of life, marked by marine regression, the weakening of reefs, the gradual disappearance of eurypterids, and the emergence of the first terrestrial forests and jawed fish. This period, though brief, laid the groundwork for the biological revolution of the Devonian, preparing a world where vegetation and vertebrates would fully flourish. Thanks to technological advances and paleontological research, our understanding of this evolutionary pivot refines every day, revealing the multiple facets of a transforming Earth. The Silurian was marked by major biological innovations that transformed the plant and animal world. We will focus on these innovations, leaving aside previous or subsequent events. The journey begins with the appearance of vascular systems in the first terrestrial plants, continues with body armors and swimming mechanics of jawed vertebrates, and concludes with the complex trophic networks of Silurian ecosystems. Imagine walking along ancient shores hundreds of millions of years ago, discovering how these innovations shaped a world in the midst of evolutionary fervor. At the start of the Silurian, the Earth was recovering from past upheavals, allowing the expansion of more organized and resilient organisms. In an environment where sea levels varied, shores and coastal areas offered a favorable ground for the conquest of emerging lands. It is here that key innovations developed. The plant world, still limited, began adapting to terrestrial life, while aquatic creatures developed musculature and armor for better mobility and protection. Simultaneously, new levels of the food chain emerged, illustrating the complexity of relationships between predators and prey. Through this narrative, we will explore these innovations and their scientific significance. Before the Silurian, life thrived mainly in the oceans. The first terrestrial plants were rudimentary, lacking sufficient structures to resist desiccation, mechanical stress, and gravity outside of water. These ancestors often measured just a few centimeters and were confined to very humid environments. However, in the Silurian, plants developed vascular systems, internal networks for the transportation of water and nutrients more sophisticated than anything that existed before. These networks were composed of specialized cells with reinforced walls. Tracheids are elongated cells that form internal conduits to transport raw sap, meaning water and minerals, from the soil to the plant. In the Silurian, they already had reinforcements in their cell walls. Simply put, these tracheids are small rigid tubes that support the plant while improving water circulation over great distances. This dual function allows plants to rise above the ground to capture more light and better manage mineral and water intake, even in less humid environments. A plant that stands tall thus benefits from better sunlight exposure, promoting more active photosynthesis and faster growth, a key step in the colonization of emerging lands. Another major aspect in the rise of the first vascular plants is the formation of an external protection, the cutin. This waxy substance covers the plant surface and acts as a barrier against water loss. Imagine a thin yet waterproof film that prevents the rapid evaporation of water from internal tissues. Without this protection, plant tissues would dry out quickly, especially in environments far from water sources. This layer, also called the cuticle, is still present in most land plants. In the Silurian, the emergence of cutin enabled plants to survive in drier environments, paving the way for them to spread beyond wet zones. The vascular innovation of the Silurian accompanies the development of small, leaf-like organs, although still rudimentary. Some plants develop small outgrowths to capture more light. At the same time, these plants create spores less dependent on continuous immersion, thus allowing dispersal over larger territories. Cryptospores, or simple spores, are found in numerous Silurian deposits, illustrating the increasing diversity of terrestrial plants. These modest advances pave the way for the future rise of forests. The primitive vascular systems and cutine protection mark a crucial step, the start of vegetation beyond the waters, capable of surviving in drier air and thriving on new soils. This advancement is not a mere detail. It forms the foundation of a terrestrial ecosystem, shaping soils, capturing carbon dioxide, and initiating diversified food chains. Animals will depend on this vegetation for nourishment and shelter. In the long term, vegetative cover alters soil composition, stabilizing the surface and creating the humus necessary for the growth of more evolved plants. Let's dive back into the water to discover a major Silurian advancement for our vertebrate ancestors: the acquisition of body armor and structures adapted for swimming. Armored fish, covered with bony plates, begin to spread. This type of protection appears in agnathan fish and early gnathostoms. However, it is primarily in basal gnathostoms, ancestors of bony fish and sharks, that we see the emergence of denticulate dermal bones and connected pectoral fins, providing them with sturdiness and better maneuverability in the water. Dermal bones, arising from the ossification of the skin, are bony plates distributed on the body, sometimes covered with small spikes or denticles. These denticles, similar to serrated scales, reinforce the armor, deter predators, and improve hydrodynamics. Unlike modern bony fish, which have an internal skeleton and flexible scales, these Silurian animals possessed a true external shield. This armor protects vital organs and supports muscles and fins. In shallow waters, prone to strong currents or predators, a body cuirass was a crucial advantage for survival. Alongside the emergence of armor, swimming also saw major improvements. Primitive Silurian fish developed more robust pectoral fins with better defined internal bony structures. Jointed pectoral fins feature a bony base, connecting these fins to the scapular girdle, allowing the fish to more precisely control its lateral and vertical movements, thus offering superior agility in the water. These improvements are linked to the need to escape more efficient predators and to hunt more agile prey. In a dense ecosystem, the gradual evolution of the skeleton, musculature, and fins is crucial to securing a place in the food web. Reinforced bony plates, associated with a perfected swimming system, offer an ideal compromise, enough mobility to hunt or flee, and effective protection against frontal attacks. At this time, the exploration of freshwater begins to develop. Although the majority of Silurian fish live in the seas, some groups frequent estuarine or lagoon areas, subjected to variations in salinity. The armor becomes an adaptive response to these environments. In shallower waters, rich in obstacles, it offers crucial protection for navigating, sneaking, and reproducing. This evolution of armors and locomotion marks a fascinating turning point in the history of vertebrates, laying the groundwork for future diversification that will lead to modern fish, amphibians, and later, terrestrial vertebrates. Let's dive into the heart of Silurian life to see how innovations shape trophic networks, that is, food relationships within the ecosystem. During the Silurian, powerful predation chains form, linking the largest predators to invertebrates like trilobites, brachiopods, and corals. To understand the dynamics of these complex networks, several factors must be considered: the availability of resources, the diversification of prey, and the evolution of hunting strategies. In the Silurian, trilobites, widespread arthropods in the seabed, are a prime prey for many predators. They feed on small sediment organisms and sometimes shape the microtopography of the seabed. At the top of the trophic network are armored fish and eurypterids, large predators with pincers and a robust body, capable of seizing prey almost as large as themselves. The eurypterids, or sea scorpions, are formidable predatory arthropods that occupy various coastal environments. They often hide in shallow waters, stalking their prey. With a segmented shell, anterior pincers, and sometimes a stinger, they are well adapted to active predation. Depending on their size, they hunt small organisms or medium-sized armored fish. At this time, several ecological niches form, each species seeking to optimize its feeding and locomotion. These interactions create a genuine food web where everyone can be a predator or prey, depending on the situation. Armored fish are distinguished by bony plates, protecting the head and shoulders. Some, in the process of diversification, will later become formidable carnivores, developing hunting strategies based on biting. These plates protect them from the claws and jaws of rivals, while their reinforced fins allow them more precise movements in the search for food. Their rise coincides with an increased availability of marine prey, like shelled invertebrates. This predator-prey relationship leads to an arms race. Prey develop defenses, and predators perfect their capture techniques. However, the environment regulates this dynamic, like the availability of oxygen or water temperature, which influences the primary productivity of algae and aquatic plants. The third major member of this complex trophic network is constituted by orthochonic nautiloids, cephalopods, with an elongated cone-shaped body. Related to present-day octopuses and squids, they have an outer shell. Thanks to internal gas-filled chambers, they move by propulsion and control their buoyancy, allowing them to hunt a wide variety of marine organisms. Sometimes, they compete with other predators, but also become prey for large armored fish and eurypterids. Nautiloids occupy a median place in the food chain, showing the increasing complexity of marine trophic networks. To survive, each lineage must adapt to the environment and the ever-renewing strategies of its competitors. Brachiopods and corals, though mostly immobile, are highly abundant and lead a passive lifestyle. Corals, living in colonies, form reefs that provide shelter and food to numerous marine organisms. Brachiopods, small animals with two shells, feed by filtering, often quietly anchored at the bottom. However, these invertebrates are not safe from predators. Corals can be parasitized, and some mollusks or arthropods attack their skeletons. Brachiopods have to defend their shells against predators. Moreover, environmental fluctuations like oxygen depletion affect their survival. These interactions show how food webs reflect constant competition, where the innovations of some exert evolutionary pressure on others. The beauty of this period lies in the fragile balance between predators and prey, favoring the opening of ecological niches and the diversification of life forms. Advances such as the vascular systems of plants, protective cutin, ossified plates, and articulated fins are not isolated accomplishments, but part of a global movement. Life seeks to explore new environments and transform itself. Photosynthetic organisms, by colonizing shores, create new sources of food and shelters for animals in tidal zones. This plant availability, coupled with the diversity of marine invertebrates, enriches the food webs. In return, the presence of predators pushes prey to develop better defenses and new escape tactics. Exploring Silurian life highlights the importance of plant vascular systems, armored features, improved swimming methods, and complex food webs. Without these innovations, the terrestrial and aquatic diversity of subsequent eras could not have developed in the same way. These advancements are interconnected. Plants modify their environment, adding layers to the food pyramid, while vertebrates and arthropods develop more complex protections and locomotion, stimulating other living groups. Each of these advances faces environmental constraints requiring constant adaptation. The Silurian thus presents itself as a laboratory, testing the viability of these innovations that will later be preserved and improved by future generations. The development of reinforced tracheids and the cutin barrier allowed plants to gradually colonize emerging lands. Though it's hard to imagine the leap represented by these internal channels capable of raising sap a few centimeters, they will later enable giant trees to draw water from several meters underground. It's not just a change in dimension, but the promise of vast terrestrial ecosystems, with animals transitioning from marine life to an existence shared between land and water. In aquatic animals, specialized armors and fins herald an even more diverse reign. Dented dermal bones, besides their defensive role, foreshadow the variety of scales and skin structures found in many vertebrates. Pectoral fins illustrate the transformation of simple protrusions into robust elements capable of supporting muscular forces. These fins signal the future evolution of limbs, starting with sarcopterygian fish, which lay the groundwork for adaptation to terrestrial life. The emergence of complex food webs shows how nature constantly balances and adjusts itself. The Silurian sees the multiplication of dietary relationships among trilobites, brachiopods, corals, armored fish, sea scorpions, and nautiloids, forming an interconnected ecosystem matrix. Some filter or graze, others hunt, attack, or develop defensive shells or camouflage strategies. These interactions show that evolution results from cross-influences, where one's innovation stimulates another's. This creates a perpetual engine. As predators become stronger, prey strengthens itself, thus enriching the overall biodiversity. This dynamic was already shaping Silurian oceans, turning them into crucibles of adaptation. Imagine yourself at the bottom of a Silurian bay. The ground is covered with calmly open brachiopods filtering the water. Nearby, trilobites sift through the sediments to uncover organic matter, while nautiloids float above them. Suddenly, a large armored fish with bony plates and jaws ready to attack makes its appearance. Further away, a eurypterid hides behind a rock, its appendages searching for prey. Who will survive that day? It all depends on the complex relationships they've established. In an instant, you grasp the essence of the Silurian, a world in transformation where new ways of feeding, moving, and defending redefine the balance of the ecosystem. Paleontological discoveries continue to clarify the adaptations of the Silurian. Fossils, conserved in particular deposits, reveal fascinating details. Imprints of plant stems with vascular channels, fragments of bony plates from primitive fish, or traces of bioturbation, indicating burrowing organisms. Paleobotany, paleozoology, and rock chemistry combine to offer an increasingly precise picture of this era and the speed at which these innovations spread. For example, one can detect traces of cutin in fossil sediments, or reconstruct the microstructures of tracheids, confirming their presence as early as the Silurian. From an evolutionary standpoint, these biological innovations set the stage for the next steps. Plants capable of growing outside water create new stable soils along the shores. These soils will be colonized by small invertebrates, before in the Devonian, other vertebrates permanently leave the water. This process gradually transforms the land surface into habitat rich in diverse life. In the water, fish reinforce their internal skeleton, reorganize their bony plates and scales, dreaming of future oceans and rivers. Eurypterids, meanwhile, will dominate the coasts until new evolutions shift the ecological balance. These advances illustrate a fundamental characteristic of life, the capability to innovate and adapt, even in an already complex environment. When plants introduce innovations like cutin, the entire ecosystem feels the impact. Less dependence on water, expansion of habitable zones, and new organic resources. Similarly, when armored fish perfect their jaws, the invertebrates must adjust to survive. This perpetual race has shaped natural history for billions of years. The Silurian, far from being a mere step, is a perfect example of this process, where life begins to colonize the land more assuredly, while aquatic life diversifies in new directions. The Silurian was a crucial stage in the history of life, marked by fundamental innovations that shaped both the plant and animal worlds. The appearance of vascular systems in the first terrestrial plants, the development of body armor and articulated fins in fish, as well as the complexity of trophic networks, laid the groundwork for the biodiversity we know today. These advances testify to the power of natural selection and the capacity of life to adapt in the face of environmental challenges. Observing the richness of modern ecosystems, from forests to reefs, we pay tribute to the pioneers of the Silurian, whose innovations continue to echo in every living organism. Thus, the study of this period is not limited to mere scientific interest, but reveals the creative and evolutionary force still at work in our biosphere. Imagine a world where vast oceans cover much of the land, with no ice masses at the poles to limit the expansion of the seas. During the Silurian, Earth resembles a climatic laboratory where ecosystems experiment with new balances. The greenhouse effect is indeed present, but less intense than during other periods, such as at the beginning of the Ordovician. Specialists often speak of an attenuated greenhouse effect, as the concentration of carbon dioxide is about 6 times higher than today. Currently, CO2 in the atmosphere is close to 400 ppm, but imagine it multiplied by 6. This creates an atmosphere much more loaded with greenhouse gases than that of our industrial era, without reaching the extreme peaks of other eras. The carbon dioxide concentration in the atmosphere keeps the planet at a temperature much higher than the current average of 15 degrees Celsius. In the Silurian, the global temperature was therefore higher. No permanent polar ice cap existed, lacking the cold conditions necessary to accumulate ice. The terrestrial landscape was dominated by flooded coastal areas, with lowlands regularly submerged by the oceans. The edges of these inland seas were inhabited by an abundant aquatic fauna and emerging flora, still rudimentary, but crucial for the future ecological evolution of the globe. The warm and humid climate of the Silurian favored the development of living communities in shallow seas, which sometimes covered entire continental shelves. Precipitation was more abundant in some regions, feeding large rivers with regular flow. Without polar ice caps, the sea level was high, creating vast coastal lagoons and estuarine zones where freshwater and saltwater mixed, carrying sediments and nutrients in abundance conducive to life. Thanks to the warmth of the water and the oceanic circulation of that time, nutrients spread across vast areas. The sun-illuminated seas rich in corals, stromatoporoids, and algae, which built reefs and participated in primary productivity. Marine life proliferated in complex ecological networks, with bony-plated fish and the first jawed fish sharing the space with invertebrates. On land, the first vascular plants, still difficult to establish, began to retain sediments, slowly modifying the banks and deltas. This warm climate became an incubator for many emerging biological innovations in the Silurian. In this carbon dioxide-rich atmosphere, another major upheaval was taking place in the depths of the Earth. The tectonic plates of the time, such as Avalonia, Baltica, and Laurentia, moved and collided, forming the Caledonian mountain ranges. These mountains, now eroded, were once imposing. To imagine their formation, one can think of the collision that created the Himalayas, although, during the Silurian, the configuration of the continents and the atmosphere was very different from today. The Caledonides, traces of which can still be found in Europe and northeastern North America, resulted from accretion and subduction events bringing ancient continental blocks closer together. This orogenic uplift, a slow and colossal tectonic movement, formed reliefs that, as they rose, exposed slopes to erosion. Rivers transported enormous quantities of sediments, forming morass deltas, typical of post-orogenic basins. This mineral mixing continuously altered coastal and submarine habitats, influencing the distribution of animal and plant species. As the planet warmed with the increase of carbon dioxide, occasional climatic fluctuations disrupted the balance. Researchers discovered in the geological strata of the Silurian signs of anoxic phases, where oxygen levels were low in some ocean basins, alternating with more oxygenated phases. Dissolved oxygen is essential for the respiration of marine organisms, such as primitive fish, mollusks, crustaceans, and some giant eurypterids. When oxygen decreased, vast underwater expanses became uninhabitable for much of the fauna. Corals, brachiopods, mollusks, and other creatures sometimes disappeared locally, while more resistant species proliferated in oxygen-depleted waters where competition was reduced. The sediments deposited during these anoxic periods are often dark, indicating the presence of undecomposed organic matter due to lack of oxygen. Conversely, during oxic phases, oxygen returned, reoxygenating the water and allowing various forms of life to recolonize these spaces. This cycle of disturbances repeated at regular intervals and can be read in the rock through fossils and isotopes. Each of the major phases of upheaval in the Silurian marked marine populations and coastal ecosystems. The Ordovician event, named after a site in Scandinavia where evidence was found, led to significant changes in ocean chemistry and marine currents. Conodonts, small marine organisms with denticulated elements, serve as biochronological markers, while graptolites, fossil colonial animals, are particularly sensitive to oxygenation changes. These disturbances reveal rapid changes in environmental conditions caused by a warm climate, variations in sedimentary inputs, and a possible reorganization of oceanic circulations. The oceans experience occasional transgressions and regressions. Sometimes the sea invades the continents, then retreats, altering the extent of the coastal zones. These fluctuations alternate between episodes where water is laden with sediments and nutrients, and others where salinity and temperature vary, impacting the entire food chain. Subsequently, the Mulda event occurs. Fossils show a drop in biodiversity among certain pelagic groups, with the disappearance or decline of graptolites. Reefs, notably those with stromatoporoids, are altered by sedimentation and dissolved oxygen. This phase, sometimes seen as an extension of the Ordovician event, is not a simple repetition. Volcanism could have released cooling aerosols or carbon dioxide, disrupting the climate. Concurrently, the formation of the Caledonides reconfigured the continents, disrupting oceanic circulation and imposing new wind regimes. These changes caused imbalances in the distribution of oxygen and nutrients, leading to abrupt expansions and depletions of marine life. Then comes the Llandovery event, the third major upheaval of the Silurian, which combines changes in the isotopic composition of carbon and decreases in oxygen in the oceans. Geologists analyze the carbon isotope ratio 13/12, which varies according to the amount of organic matter deposited on the seafloor. During the Llandovery event, this ratio peaks, accompanied by massive deposits of black, oxygen-poor sediments, a sign of large-scale anoxia. Some groups, such as crinoids and brachiopods, decline sharply or even disappear. This reorganizes marine communities, altering competition and allowing surviving species to diversify into freed niches. This cycle of crisis and recovery makes the Silurian a period of significant evolutionary mixing, where nature multiplies adaptation strategies in response to an unstable environment. The Ordovician, Mulda, and Lau events show how moderate greenhouse effects, combined with a changing geography, can cause recurring pulses of anoxia and oxygenation. These phenomena do not affect all seas in the same way. Some poorly connected regions or those overloaded with organic sediments switch more easily to anoxia, while others, better ventilated, remain stable. Species surviving in these hostile environments often have specific strategies, tolerance to low oxygen or absence of predators. But as soon as an oxic phase returns, competition intensifies. If they do not adapt, they decline. This alternation game gives the Silurian fossil record a sawtooth appearance, marked by rapid appearances and disappearances of numerous groups. To understand these oxygen variations, the impact of volcanism and its climatic effects via carbon dioxide must be considered. Eruptions project dust and gases. The dust causes temporary cooling by reflecting solar energy, while carbon dioxide leads to long-term warming. These climatic alternations directly influence the solubility of oxygen. The warmer the water, the less it retains, creating depleted zones. Simultaneously, changes in oceanic circulation, due to the reorganization of continents, disrupt the supply of nutrients on continental margins, affecting the entire food chain. Thus, although the Silurian is overall warm, it is marked by local and regional crises, accentuated by continental collisions, such as during the formation of the Caledonids, causing massive extinctions in oxygen-deprived areas. The Caledonian uplift plays a major role in these fluctuations. The collision between Avalonia, Baltica, and Laurentia forms mountains that discharge significant volumes of sediments into neighboring basins. Molasse deltas, resulting from the erosion of these reliefs, pour into coastal areas and feed major watercourses. In the short term, these inputs stimulate marine life by enriching plankton, but in excess, they clog reefs, disturb the water column, and trap organisms unable to adapt. The decomposition of organic matter consumes oxygen, worsening anoxia. This interaction between erosion, sedimentation, temperature, and oxygen conditions the survival of Silurian species and reshapes their global distribution. In the Silurian, life itself influences the chemistry of the oceans and the atmosphere. Algae, through photosynthesis, consume carbon dioxide and release oxygen. Even in anoxic environments, certain bacteria alter water chemistry. The carbon cycle is thus closely linked to organisms. Their remains form sediments that store carbon in the long term. This loop creates positive feedback. The more life develops, the more carbon dioxide can be extracted from the atmosphere. But anoxic crises interrupt this process. By killing fauna and slowing photosynthesis, they limit the ocean's capacity to sequester carbon. How hot was it in the Silurian? The absence of polar ice caps indicates equatorial regions probably around 30 degrees Celsius, according to paleoclimatic estimates. Temperate zones were milder and wetter, although the distribution of land and seas differed from today. Coral reefs extended to high latitudes, proof of waters warm enough to allow calcification. Even near the poles, it was not cold enough to maintain permanent ice caps. The planet thus offered a globally warm climate, dominated by vast temperate seas and crisscrossed by powerful rivers, continuously carrying immense quantities of sediments. Although weaker than during other periods, the greenhouse effect in the Silurian remained well above today's levels. Rocks from the time reveal variations in the carbon isotopic index correlated with extinction waves and marine life readjustments. Conodonts, key fossils for dating, see their populations drop during the Ordovician, Muld, and Lau events. After each anoxic crisis, the most resistant corals and stromatopores colonize vacant substrates. This constant renewal gives rise to original reefs, shaped by the alternation of brutal destruction and opportunistic reconquests. The pelagic fauna, composed of primitive vertebrates and swimming arthropods, must constantly adapt to environmental upheavals. After each anoxic crisis, vacant niches allow some species to diversify rapidly. This cycle of partial extinction, followed by adaptive radiation, marks Silurian biodiversity. Fossils show the emergence of new forms and the proliferation of previously inconspicuous species. These transformations alter the structure of ecosystems. New predators appear, prey develop, and former dominance decline, thus redefining trophic hierarchies through the crises. The Caledonian uplift also influences chemical erosion. New mountains expose fresh rocks, which react with air and water, consuming carbon dioxide to form carbonates. This process, in the long term, can partially offset volcanic emissions. In the Silurian, it helps maintain a high level of CO2, but can also cause temporary local cooling, altering ocean circulation and dissolved oxygen. This complex interplay of interactions helps researchers understand the combined effects of volcanism, erosion, and anoxic crises on the environment. The Silurian is a theater of processes that will also mark subsequent periods at varied rates. The alternations of anoxia and reoxygenation reflect a key mechanism. The ocean, an oxygen reservoir, depends on exchanges with the atmosphere and biological productivity. Any climatic or tectonic disturbance propagates and affects vast regions. The Caledonian collision alters the geography of continents and basins, disrupting currents and sedimentation. Biological communities then must adapt, thrive, or disappear. The Silurian was a pivotal epoch, where moderate greenhouse effects associated with the formation of the Caledonian mountain ranges shaped the climate in marine and terrestrial habitats. Repeated cycles of anoxia and reoxygenation in the oceans posed major ecological challenges, leading to successive losses and rebirths in marine biodiversity. This constant dynamic between crises and opportunities forged the complexity of ecosystems, where life, in constant adaptation, was able to exploit each variation to diversify. The Silurian thus illustrates the close link between geological, chemical, and biological processes, reminding us of the fragility, but also the resilience of the Earth and its inhabitants in the face of the changing rhythms of climate and tectonics. Some fossiliferous deposits stand out for their exceptional preservation of organisms, whether marine, terrestrial, or intermediate. These sites are sedimentary deposits offering remarkable concentration or quality of fossils. In the Silurian, a period marked by significant biological innovations, the Lagerstätten are unique temporal windows, allowing us to dive into the life of ancient ecosystems and to understand the diversity of the living world at the time. This chapter will take us on a journey across 5 fossiliferous sites, classified chronologically in the United States, China, the United Kingdom, Sweden, and the Czech Republic. We begin our exploration in Waukesha, in what is now the state of Wisconsin, in the United States. Today continental, this region was partially covered by a shallow epicontinental sea 437 million years ago, during the Silurian. The waters, probably around 20 degrees C at certain times of the year, were relatively warm, although these estimates vary according to paleoclimatic reconstructions. In this context, marine sediments accumulated, trapping within their layers a diversity of life forms, from invertebrates to early arthropods. One of the major discoveries at Waukesha is the oldest known scorpion in the Silurian fossil record. Although scorpions are terrestrial arthropods, their ancestors were likely amphibious or marine. The specimen found at Waukesha shows the transition to a terrestrial lifestyle with anatomical features adapted to a partially aquatic environment. For example, their respiratory organs were not fully adapted to breathing in open air, and they probably sought out humid environments to survive. Much smaller than their current descendants, these scorpions were probably not formidable predators, but their presence indicates a progressive conquest of shallow and terrestrial environments. Another notable group in Waukesha is the complex chitinozoans. These small microfossils, generally ovoid or spherical, are made of chitin, a resistant organic substance. They are often considered to be the capsules of zooplankton, although their exact nature has long been debated. The term complex describes the morphological diversity observed in chitinozoans from Waukesha, indicating advanced evolution in the Silurian. These fossils, often invisible to the naked eye, require meticulous preparation techniques such as electron microscopy. Chitinozoans are essential biostratigraphic markers because their distribution in sedimentary layers allows precise dating of the strata. At Waukesha, their abundance and diversity provide valuable insight into Silurian plankton, a key part of the marine food chain. The Waukesha Lagerstätte is crucial for understanding Silurian fauna and the early transition of arthropods to land. It also reveals the complexity of planktonic ecosystems thanks to the chitinozoans, while showing the diverse adaptations of organisms to marine variations. The remarkable preservation of this site is due to sedimentation conditions, probably anoxic or weakly oxygenated, which allowed the conservation of delicate remains such as scorpion cuticles and the organic walls of chitinozoans. We now move to Huangshi in southern China, dating back 435 million years. This paleontological site features a faunal assemblage from a subtidal environment where light diminishes and oxygen fluctuates. These black shales, characterized by fine clay sediments, are associated with low circulation of oxygenated water. Under these conditions, the carcasses falling to the bottom were quickly covered and preserved, which explains the exceptional quality of fossilization. In Huangshi, sponges were among the dominant groups. These primitive organisms, which form the basis of many current reefs, could also thrive in deep waters during the Silurian. Although they have neither differentiated organs nor a nervous system, sponges possess an internal skeleton made of minerals or elastic fibers. Their key role in the marine ecosystem is to filter water. By pumping large volumes of water, they capture food particles and help clarify the water column. In the Silurian, they were already well diversified with varied forms, allowing them to occupy multiple ecological niches. Even though sponges dominate, there are also other animals, such as cephalopods, ancestors of squids, octopuses, and ammonites, as well as marine arthropods resembling small crustaceans. These creatures evolved in an environment marked by intermittent oxygenation, where oxygen was not always sufficient to support a great diversity. Thus, only species most tolerant to low oxygen levels could thrive. The Huangshi Lagerstätte is crucial for understanding how marine life thrived despite potentially stressful conditions. Paleontologists analyze the chemical composition of sediment layers to study phases of oxygenation and oxygen deprivation. Another remarkable point is the preservation of sponge spicules, those tiny needles, which offer researchers a better understanding of sponge diversity in the Silurian. By studying their evolution, we better assess their ecological impact and adaptation to hostile environments. We continue our journey back in time, stopping at a time 430 million years ago in what is today Herefordshire, in the west of the United Kingdom. This Lagerstätte is famous for the quality of preservation of its fossils, notably organic molecules and delicate structures that would quickly decompose elsewhere. Thanks to the particular conditions of deposits, with fine sediments and favorable diagenesis, some species are preserved in 3 dimensions. This quality of preservation is rare, as most fossils are often crushed or fragmented under the pressure of the strata. In Herefordshire, several enigmatic mollusks have been discovered, such as Puncthyrox and Vorticautum. These mollusks, with elongated bodies and complex internal organization, attract researchers' interest. Mollusks, a highly varied group including bivalves, gastropods, and cephalopods, here present particular anatomical features, powerful muscles, dorsal protective structures, and varied feeding systems. Research suggests that they occupied specialized microhabitats, feeding on small organisms present at the bottom or in the water column. The Herefordshire Lagerstätte is also famous for its 3-dimensional ostracods. These small crustaceans, protected by a calcareous bivalve shell, are normally found in the form of valves, as their soft tissues rapidly decompose. But in Herefordshire, thanks to exceptional fossilization conditions, one can observe not only the shell, but also the interior of the body, including the legs and mouth parts. This allows researchers to better understand their lifestyle, diet, and locomotion. Techniques such as tomography, which involves taking X-ray images to create a 3D model, are used to reconstruct these microcrustaceans and visualize their internal organs. These data improve our understanding of their anatomy, distribution, and evolution in the Silurian. They highlight the importance of Lagerstätten for documenting life forms often reduced to fragments. In sum, Herefordshire perfectly illustrates what 3-dimensional fossilization brings: the opportunity to examine the complete anatomy of ancient animals in detail. The fossils of Puncthyrox and Vorticautum testify to the inventiveness of life, while the 3-dimensional ostracods reveal internal structures otherwise invisible. This region of the United Kingdom is thus an ideal place for researchers wishing to reconstruct ancient ecosystems and understand the biological diversification of the Silurian. We now travel to Brunspar in Sweden, where fossils dating back 427 million years attest to the importance of graptolites in this Lagerstätte. Graptolites were extinct marine colonial animals that crafted tubular structures from a protein similar to chitin called graptolite collagen. Each colony, or rhabdosome, was composed of many small chambers, housing individuals called zooids. Depending on the species and the era, graptolites could be planktonic or attached to substrates. In Brunspar, there are colonies of tree-like graptolites, resembling small trees or bushes. The term monospecific means that all the chambers of the colony belong to the same species without mixing with other types. Although this seems logical, some sites show colonies where several species mix due to successive deposits or movements. Here, the clear arrangement and purity of the species indicate that the colony developed as one unit. The graptolites from Brunspar are exceptionally well preserved, allowing for the distinction of their stipes and the arrangement of the chambers. This precision enables paleontologists to study their feeding and reproduction. It is believed that, for the most part, they feed by filtering. Each zooid captured food particles in the surrounding water. Their fan-like or tree-like shape helped optimize water flow, like a sail catching the wind. The study of these colonies also highlights the changes of the Silurian, where variations in sea level, ocean chemistry, and interspecies competition influence the geographical distribution and morphology of graptolites. The location of Brunspar in Sweden showcases one of the areas where the marine biodiversity of the Silurian was sustained and transformed on the Baltic Plate. At this time, the geography of the planet was very different, with continental masses arranged differently. Graptolites, with their planktonic lifestyle, could travel great distances, carried by currents. The importance of Brunspar lies in its ability to reveal the precise spatial organization of a single colony, illustrating the plasticity of graptolites and their ability to thrive in waters where salinity, temperature, and oxygen fluctuated. To conclude our tour of Silurian Lagerstätten, we stop at Kwanti in the Czech Republic, where nearly complete acanthodian fish fossils have been found. Dating back 423 million years, this site is particularly remarkable. Acanthodians, or spiny fish, are a group of primitive vertebrates that played a major role in the evolution of fish and gnathostoms, jawed animals. Acanthodians are recognizable by their numerous spines supporting the fins, present at the pectoral level, along the body, and sometimes on other accessory fins. Anatomically, they occupy an evolutionary crossroads between jawless fish, like lampreys, and those with articulated jaws. At Kwanti, the nearly complete specimens offer an exceptional glimpse into their skeleton, dermal armor, and internal organization. Although most measured only a few dozen centimeters, larger forms exist in other deposits. The vertebral column, the pectoral and pelvic girdles, as well as the nascent jaws and their small teeth, are distinct. This discovery highlights the key adaptations that allowed jawed fish to become dominant in aquatic environments. The emergence of jaws transformed predatory interactions and the diets of these vertebrates, allowing them to grasp a wider variety of prey and to crush foods difficult for jawless forms to ingest. Acanthodians thus paved the way for future sharks and bony fish, which would quickly dominate the seas and freshwaters. The conditions of fossilization at Kwanti suggest rapid deposition in a calm marine environment, probably related to fine sedimentation from the erosion of mountains or coastal areas. A low oxygen content in the sediments likely facilitated the preservation of these specimens. The paleontological study of the site also reveals the diversity of marine taxa that coexisted with the acanthodians, such as brachiopods, trilobites, as well as algae and microorganisms. Scientists are also interested in predation relationships. Some bone fragments and bite marks indicate that even these spiny fish could be attacked by larger or more agile predators. The discovery of nearly complete specimens at Kwanti is crucial for understanding the paleobiology of acanthodians. In museums, fragments like spines or scales are often found without being able to reconstruct the general shape of the animal. At Kwanti, the preservation of intact skeletons allows reconstitution of the overall appearance, distribution of fins, and spines. Bone microstructures, analyzed under a microscope after polishing, reveal information about their growth, vascularization, and the composition of their mineralized tissues. Beyond morphology, these acanthodians tell the story of a fauna growing in complexity in the Silurian seas, initiating the conquest of aquatic ecosystems by jawed fish. These 5 Lagerstätten offer a unique window into the diversity and evolution of Silurian marine ecosystems. Thanks to remarkable preservation, these sites allow detailed study of extinct lineages, from amphibious arthropods to jawed fish, and a better understanding of how life adapted to environmental fluctuations. The analysis of these fossils sheds light on major biological innovations of the time and confirms that the Silurian, long perceived as stable after the Ordovician, was in fact a dynamic period, rich in innovations and ecological reorganizations. These discoveries enhance our understanding of the complexity and resilience of ancient ecosystems while embedding the Silurian in the fundamental tapestry of life's history. Now, we will explore several major paleontological discoveries made between 2024 and 2025, all related to the Silurian. Imagine a passionate guide taking you into a universe hundreds of millions of years old, but still a dynamic field of research. We will start with the recently described vermiform aculiferan mollusks, then dive into the dark shales of Huangshi to study episodic oxygenation of these ancient environments. We will then analyze a binotocope ostracod revealed through 3-dimensional reconstruction, revising our hypotheses about their locomotion. We will continue with the study of new organic carbon isotope curves, offering high resolution on the environmental fluctuations over 400 million years ago. Finally, we will end with the discovery of gigantic specimens of Australian eurypterids, redefining their biogeography. First theme, the vermiform aculiferan mollusks, elongated-bodied animals, sometimes referred to as worms, but with spiny or reinforced external structures. 2 species, Punc-ferox and Amo-vorticautum, recently described in an article forthcoming in 2025 in Nature, have particularly attracted researchers' attention. These original names reflect the spiky nature of these creatures. The term aculiferan refers to a group of mollusks that do not have a massive shell, but rather small plates or spicules forming their protection. In Punc-ferox and Amo-vorticautum, the vermiform body is covered with these rigid elements, thus offering increased defense against predators. The article forthcoming in Nature highlights the unexpected complexity of the muscular mantle of Punc-ferox and Amo-vorticautum. This mantle, a tissue covering the body of mollusks, serves to secrete shells and protections. In these 2 species, a highly branched muscular network, more elaborate than expected, was observed. This shows that, as early as the Silurian, some mollusks possessed sophisticated musculature in a multifunctional mantle. This discovery contradicts the idea of prevailing simplicity at the time. These vermiform forms reveal that the selective pressure in Silurian waters favored complex internal structures, useful for locomotion, feeding, and defense. Imagine the life of these elongated animals during the Silurian in shallow marine environments, sometimes dotted with reefs. Forms without a robust shell, like those of arthropods, had to find other means of protection. The evolution of mineralized plates, spicules, and reinforced muscle areas allowed them to withstand predators. This changes our view of the trophic dynamics of the time. Some organisms opted for fragmented armors, thus preserving relative mobility. The diagrams and plates to be published in Nature in 2025 will illustrate the comparative anatomies of Punc-ferox and Amo-vorticautum, revealing ingenious survival strategies in a competitive environment. Moving on to the fauna of Huangshi, recently studied in works published in 2025 by the Geological Society of America. This site, located in southern China, is a significant Silurian deposit. Researchers have intensified their studies to understand the environmental conditions that prevailed at the time. The shales of Huangshi, known for their dark color, bear witness to the abundance of organic matter during their sedimentation. This suggests anoxic periods, where the lack of oxygen complicated the sustainable establishment of benthic fauna, meaning those living on the seabed. The novelty of the 2025 work lies in the discovery of signals of occasional oxygenation. These seemingly anoxic black shales occasionally experience transient episodes with more oxygen. How did they prove it? By studying microfossils, the chemical composition of the sediments, and the distribution of larger fossils, such as sponges or cephalopods. Sponges require a minimum of oxygen to live. Their presence at various geological levels shows that the water was not constantly devoid of oxygen. Temporary events thus allowed a richer fauna to develop before disappearing during local fluctuations. This finding is crucial, as the fauna of Huangshi includes species classified as biological refugees during intense anoxic phases. These refugees offer more favorable conditions within a hostile environment. By studying them, we reconstruct the adaptation strategies of sponges, cephalopods, and arthropods. The GSA 2025, by highlighting these windows of oxygenation, refutes the idea of a consistently anoxic environment. This reassesses our hypotheses on ocean productivity, current circulation, and climate impact. The implications go beyond paleontology. Understanding the persistence of life in extreme conditions sheds light on the resilience of ecosystems. The third major point of our recent discoveries concerns a binotocope ostracod equipped with detailed appendages, whose publication is scheduled for 2024 in Royal Society Biology Letters. Ostracods are small crustaceans with a bivalve shell, often fossilized as two calcified halves resembling grains of rice. Binotocopes, a particular subgroup, stand out by the shape and positioning of certain body segments, notably the appendages. Ostracod fossils are valuable because they are numerous, well-preserved, and serve as environmental indicators. Their presence, diversity, and morphology reveal a wealth of information about ancient aquatic environments. Until now, the knowledge of the internal appendages of Paleozoic ostracods was limited, as the soft body parts are easily crushed during fossilization. Thanks to tomography and 3D numerical reconstruction techniques, researchers have been able to reconstruct the anatomical details of an exceptionally preserved binotocope specimen in Silurian layers. This reconstruction has allowed a re-evaluation of the locomotion and ecological role of ostracods. Contrary to the common belief that these creatures were primarily benthic, there are clues that they could swim actively. The appendages, initially considered sensory or manipulative, also facilitated this locomotion. This discovery sheds light on the distribution of ostracods in different paleo environments. Far from being limited to soft substrates, these crustaceans could explore the water column and even migrate over great distances. The three-dimensional preservation reveals that their shell had articulation zones, allowing larger openings than expected, which suggests they could filter water to feed on plankton. The upcoming article in Royal Society Biology Letters will detail these observations. This re-evaluation changes our understanding of the trophic networks of the time and their interactions with marine fauna. Let's move on to the mid-Homerian organic carbon isotopy, a major subject in an upcoming 2025 publication in paleogeography, paleoclimatology, paleoecology. Organic carbon isotopy measures the proportions of stable carbon isotopes in fossil organic matter. This distribution varies according to biological and geochemical processes at the time of deposit formation. In the Silurian, during the mid-Homerian, significant fluctuations in carbon-13 have been linked to major biological events, such as partial extinctions and reorganizations of marine fauna. What distinguishes this study is the temporal precision it provides. The researchers have established new isotopic curves with a resolution of less than 20,000 years, an impressive fine-tuning for a period over 420 million years old. To achieve this, they sampled very complete sedimentary successions, sometimes from different but complementary sites, and used sensitive measurement methods. These data reveal rapid isotopic variations, suggesting a faster climatic variability than previously thought. Usually, the Silurian is analyzed in terms of major trends, but here it is discovered that there might have been more subtle oscillations on scales of a few thousand years. These fluctuations in the distribution of organic carbon are related to oceanic productivity cycles, plankton population sizes, and the changing configuration of continents. During the Silurian, plate tectonics altered coastlines, communications between marine basins, and the distribution of currents. The 2025 Paleo 3 data feed finer climatic models, comparable to extinction events like Ordovician or Mulda. By cross-referencing isotopic peaks with biodiversity variations, the researchers hope to better understand the triggering factors of Silurian marine crises. This temporal precision helps untangle the impact of atmospheric composition, continents, and volcanic activity on these ancient eras. The last noteworthy point concerns the discovery of a giant Australian eurypterid, announced in Gondwana Research in 2024. Although some eurypterids exceeded a meter, this new specimen breaks a record, reaching over 2 meters. It is believed to be a pterygotide, a subfamily renowned for its impressive sizes and formidable pincers, making it a dominant predator in its marine ecosystem. What is striking in this publication is the biogeographical extension of pterygotids across the ancient supercontinent Gondwana. The Australian specimens confirm that these predators were dispersing much more widely than anticipated. The indices of trans-Gondwanan migrations found in Australia, which align with observations in South America and Africa, suggest that these eurypterids could cross vast epicontinental seas. This indicates that they evolved in a broader environment, crossing great distances, supported by favorable marine corridors or higher sea levels. From a paleontological standpoint, the discovery of large eurypterids is facilitated by lagoonal or coastal sedimentary deposits that preserve their external skeletons well. By comparing different species of pterygotids, we refine our understanding of their functional diversity. Some eurypterids had long, toothed pincers, ideal for grasping large prey, while others were more adapted to fast swimming. The analysis of imprints, joints, and wear on the pincers helps determine their diet, whether it was armored fish, trilobites, or other arthropods. These giant predators likely had a significant impact on Silurian marine communities. This new geographical extension shows that the Silurian, far from being a static period, was a time of great faunal transfers. The continents, then assembled, formed vast coastal zones, and the dynamics of plate tectonics, coupled with sea level variations, favored multiple connections. The giant fossils found in Australia suggest the existence of oceanic routes created by marine transgressions, opening temporary biological bridges. Thus, Eurypterids could travel from temperate regions to more tropical zones, making them representatives of the cosmopolitan fauna of the Paleozoic. The Silurian period is revealed to be rich in biological innovations and unexpected distributions. The vermiform aculiferous mollusks, far from being primitive, have a complex muscular system. The Huangshi shales, once thought to be anoxic, conceal habitats governed by episodes of oxygenation. Binotocope ostracods are not merely passive, but possessed active swimming abilities. Mid-Homerian organic carbon isotopy provides precise details about the climate and oceans of the time. Finally, the giant Australian Eurypterids show the dispersion of fauna via continental marine corridors. These discoveries enrich our understanding of current environmental dynamics. The extreme specializations in survival in difficult conditions remind us of the adaptive potential of life. The anoxia and oxygenation events of the Huangshi shales resonate with contemporary concerns about marine hypoxia linked to climate upheavals. The isotopic studies of organic carbon highlight the rapid variations in the carbon cycle, emphasizing the need to monitor carbon dioxide in the oceans and atmosphere. The discoveries on the geographical extension of Eurypterids highlight the impact of ocean circulation, sea level changes, and continental configurations on species dispersion. They reinforce the idea that biodiversity fronts, even in ancient times, were influenced by environmental fluctuations, and that super predators could rapidly colonize new territories. These observations connect Silurian paleontology to other disciplines such as climatology, biogeography, and geochemistry, showing the importance of an interdisciplinary approach to understanding the Earth's past. It is fascinating to see how modern technology, notably tomography, aids in major paleontological discoveries. These techniques allow for the reconstruction of muscle microstructures or appendages of creatures extinct for nearly 400 million years without altering them. Thanks to specialized scanners and software programs, the anatomies of Punk ferox, Mo vorticautum, or the Binotocope ostracod are revealed. This advancement underscores how the science of fossils, although rooted in the past, relies on modern tools. Paleontologists working on the giant Australian Eurypterids use meticulous extraction techniques, such as microdrills and needles, to free the fragmented skeletons buried in rock. Each fragment, whether it is a claw or a segment, is carefully geolocated before being reconstructed in 3 dimensions via photogrammetry. This method, which involves taking multiple photos from different angles to create a virtual model, allows researchers to analyze the complete morphology of these fossils, even when they are fragmentary. The giant Australian Eurypterids owe their size to high marine productivity, low juvenile predation pressure, or evolutionary adaptations favored by conducive conditions. The increase in marine dioxygen in the Paleozoic might also have favored these giant arthropods. Although this hypothesis is debated due to the lack of direct data for the Silurian, it remains plausible. Preliminary results from Gondwana research pave the way for future studies combining sedimentary, paleoecological, and geochemical analyses to study the impact of oxygen, tectonics, and climate on this gigantism. To summarize the extent of these recent works, the vermiform aculiferous mollusks described in Nature redefine the anatomical sophistication of animals once deemed primitive. The Huangshi shales, with sporadic episodes of oxygenation, reveal the complexity of Silurian marine environments. The binotocope ostracods, analyzed by high-resolution tomography, demonstrate more dynamic locomotion strategies than expected. The mid-Homerian organic carbon isotopic surveys, precise to less than 20,000 years, offer an unprecedented perspective on climatic and biological fluctuations. Finally, the giant Australian Eurypterid illustrates the capacity of certain Paleozoic groups to colonize vast spaces, confirming a cosmopolitan and dynamic Silurian. Each of these stories enriches our understanding of the Silurian. They show that, despite the temporal distance, current mechanisms of evolution, adaptation, and geographic diffusion already existed. Understanding how life has traversed crises, upheavals, and innovations helps us better interpret today's world and its changes. The past, key to the present, can also guide the future. By exploring punk ferox, the fauna of Huangxi, the binotocope ostracod, mid-Homerian carbon isotopy, or the gigantism of Australian sea scorpions, we touch upon the fascinating history of life. Thus, we come to the end of this visit on Silurian paleontological discoveries planned between 2024 and 2025. Beyond the technical details, it is an invitation to curiosity, for each rock layer, each fossil discovered, extends the unfinished narrative of evolution. Science progresses rapidly, thanks to revolutionary technologies or the determination of researchers sifting through geological terraces or analyzing sediment cores. These advances reveal a Silurian world far more diverse than what was thought a few decades ago. Each new discovery enriches the Silurian puzzle, testifying to a great evolutionary richness. They also underline the complexity of ecological interactions of the time. It is certain that future research will refine, clarify, or question some current interpretations. This is the nature of science, a constantly evolving path where yesterday's questions can find answers thanks to a miraculously preserved fossil or the most modern instrumentation. Finally, the Silurian provides clues about the emergence of complex marine life, intermittent oxygenation, the conquest of coastal areas, and muscular or skeletal adaptations that allowed certain groups to thrive. Over 400 million years ago, elaborate survival strategies and a great diversity occupied all ecological niches. Recent data shows that evolution has long shaped an inventive world. Too often seen as a mere bridge between the Ordovician and Devonian, the Silurian deserves a major place in the history of life. At the end of this exploration, the Silurian appears as a dynamic period, rich in anatomical and ecological innovations. The vermiform aculiferous mollusks reveal unsuspected complexity. The fauna of Huangxi illustrates variations in oxygenation. The binotocope ostracod testifies to the diversity of modes of locomotion. Organic carbon isotopy sheds light on climatic cycles, and the giant eurypterids demonstrate large-scale faunal movements. Pedagogically, these works raise awareness of the fossil heritage, highlight the importance of geology for understanding the past, and inspire wonder at the universal history of life that is constantly renewed and adapted. Thus ends our overview of Silurian discoveries from 2024 to 2025. This journey through the ages, rich in revelations, may have piqued your curiosity. When thinking of punk ferox, Emo vorticautum, or the giant Australian sea scorpion, perceive the distant dawn of marine life in a new light. The Silurian reminds us that Earth has always evolved, each stage shaping current ecosystems. Passionate researchers continue excavations and analyses, as the past still holds many mysteries. The evolutionary story is far from static. Each fossil, each isotopic signal, each skeleton brings us closer to the truth about the complex history of life. It is a privilege to reconstruct, piece by piece, the mosaic of ancient Earth.